Way back in about 2010, 2012, I was approached by a guy called Rick, I can't remember his second name, who was a friend of a guy called Kent Robinson, who was interested in me making a new crankcase half and crankshaft for his 1904 Rover Forecar. Um, now, I knew nothing about it. I didn't know how big it was, anything like that. But I said I would take a look and see if I could do anything. So I went and paid a visit to Kent in Fleet in Hampshire, and it was a very interesting visit. It took me around. He had some really interesting old cars and a 1904 Rover Forecar. The problem with it was that the crankcase was cracked. And this was caused probably by the actuation of the clutch and the way it pressed on the side of the casing, the crankcase, and just kept flexing it until eventually it broke. With it being a very early aluminium casting, it wasn't very strong. If you look closely at the picture here, you can see just around the brass or the bronze bush with the part of the crankshaft sticking out of it, around the outside of that. If you look closely, especially near the bottom rib, you'll see a crack. That crack extends all the way around, virtually right the way around to the top of the crankcase, or to the top of that circular boss. So it's quite a big crack. And the clutch is actuated on the 4-start thread, which you see on that bronze bush, and it's that actuation against that was causing flexing of the whole crankcase side, until eventually it gave up due to fatigue. And also people had not been correctly adjusting the clutch. They'd been cutting away pieces of the crankcase in order to make room for the actuating lever, when in actual fact, if they'd looked properly, that doesn't need to be done. You can loosen a screw and turn it and then tighten the screw up. Virtually, it took me a while to figure it out, but it is easily done, or was easily done. Once I'd had a chance to have a look at it, I said, okay, I will go ahead and do it. And I went out and purchased a rather large lump of aluminium alloy. I think that's about 17 inches by about 12 by 4 inches thick. Quite a sizable lump. I can't remember what it cost me at the time. It wasn't that expensive, relatively. But you can see alongside it the conrod, which was also made from solid, by the way. I found that lying in a lump of EN24 bar. That conrod is about 9 inches long in total, so you can see it's quite a sizable chunk of metal. And the next thing to decide was how was I going to go about machining it. So on looking at the original part, I thought, well, that chunk of metal is such a huge amount of waste. If I could get it profile cut, at least I would save an awful lot of time just profile milling around the silhouette of the part, if you like, which is the first sort of major step. So I drew it out on AutoCAD, and I phoned up a local company that does this jet cutting, and they agreed to do it for me. I think it was about £63, I think, to get cut. And you can see there, I supplied them with a DXF file drawing, and I took the metal down to them, and 2 days later they phoned me up and said, you can come and pick it up. And I was absolutely gobsmacked at the results. These machines are fantastic. They cut through anything. They even use them for cutting cake in factories, so that they don't disturb. And you know how you can cut a sponge with a blunt knife and it squashes everything. The same would happen if you tried even with sharp knives, but with a jet cutter, it's so violently fast that things don't have a time to get wrecked, they just get sliced through. But anyway, it made a marvellous job of it, and I had a trip around the factory at the time, and they were cutting ceramic tiles, pattern tiles, to form like a mosaic for some of these big hotels in down in Abu Dhabi and places like this. You know, their business is thriving. I don't know how it's doing these days, but it was very interesting. And as you can see, that doesn't look, that bit of metal, that doesn't look as though it's cut, but you'll see on the next few photographs just how impressive it is. I was absolutely amazed by it. And the cutter is actually angled so that the cut is truly vertical or truly square to the line that you've drawn. And I believe the divergence of the cutter is about 2 degrees maximum over a 4-inch thickness. And there you see the crankcase cut out, and also the cutout from it. Well, the first job to be done is to work on the machined round surfaces, if you like. In other words, the inside of the crankcase and the main bearing housing, and also the register face where it joins the other crankcase half. And that's all a turning exercise, and that was where I started. So we'll run through the pictures as we go. Because on. The work is so big in diameter, it won't fit in any of the chucks that I've got. So the first thing I did was to drill some holes in the back, not too deep so that it didn't go right away through the case, so that I could mount studs in there and fit it onto the faceplate of the lathe. And there you see it actually in the lathe for the first time. And again, if you look closely at this picture, what you'll see is the lug, or the mounting arm of the crankcase, is actually so far from the center of the lathe that it's catching on the lead screw, which you can see there. I ended up machining or filing a 1/16 of an inch off that, so it cleared it. I also had to actually push the chip guard at the back of the lathe away from the center of the lathe, because that was also fouling the work. So I had to bend that a little bit, so I had to actually modify the lathe so that I could get the job started. So the first processes were lathe work, as I've said. I was started by boring out the center. Initially I had to leave this boss in the center, as you can see here, because I wasn't too sure what arrangement I was going to make for the crankcase or the crankshaft to fit in there. However, I did do all of the machining on the inside, just left that boss about a 1/4 of an inch bigger than necessary until I decided what way we were going to go with the crankcase or the crankshaft, because it needed discussing with the owner as to which way was going to be the best way to do the job. Amongst the last of the jobs of the turning side of things, the lathe work, was to machine the register face where the other half fits. This sort of guarantees that your two bores will be central, will be in alignment, and it's very important that you get that right when you're making this sort of crankcase, because that is the register that makes everything true. And there you see in that picture, that's held on just by pushing it on there. It's not a great tight fit, but it locates nicely, and you can see it's not falling off. There's nothing holding that on except a little bit of friction. And finally, the last process is to bore out the center to take the bearing. I had to use the original bearing because the 4-star thread at that time was a very difficult thing to make on with my equipment, and it was just as easy to actually increase the OD of it a little bit where it went through the crankcase by putting a sleeve on and brazing it into position and reusing the same bush, which is what we did. There you can see on this picture the bearing removed from the crankcase, and you can see how much damage there's been done to the webs on the casting. They've been cut away, hacked and all sorts just to make room for the clutch lever. Real mess. Plus, in order to adjust the clutch, they thought that you had to turn the bearing to get the lever into the right position. So that's what they did. But in order to do that, they've also drilled extra holes, and you can see that the flange is covered in holes. It's obviously been resituated 2 or 3 times, and a right bloody mess has been made of the crankcase as a result. Just through poor maintenance over the years and people not really looking to see how things are adjusted properly. You certainly don't go hacking bits of casting away if you can't adjust the clutch. You investigate a bit further, surely, but obviously maybe they didn't. And not only were they was the bearing held in by screws, but they also riveted the screws over just to make sure they wouldn't come loose. So I had to dig them out with a Dremel. And there you can see, I was really surprised that the crankshaft or the crankcase half actually survived my treatment trying to get the bearing up, because it was fractured around that boss. But it survived. But you can see the ring, but you know, on the face of that crankcase, and that's where the flywheels were rubbing when the clutch was pushed in. It was moving that much; it was actually touching the flywheels. So obviously, repair was an essential thing. Well, the next phase of the operation was to take the metal and put it in or on the table of the milling machine and start milling operations. These would be linear operations, straight line operations, with it clamped to the table of the mill. These couple of shots show that quite clearly. It's being milled in straight lines, etc. You can see there that I've followed my markings for the first few parts of the milling. The next phase was to move take it off the table and start some circular motion, and because the biggest rotary table I had at the time was 6-inch, which was way too small for this, I invested in a brand new 10-inch rotary table, and that's what you see that piece of metal sat on in the next few shots. And there you see the mill generating a curved surface around the outside of the bore. If you notice that channel, it runs parallel to the table, and then it starts the right thickness. It follows the curvature of the bore. It's difficult to describe, but you can see what's meant there. You have to take a series of cuts. You can't just cut at full depth, and you notice all of those tools are extended quite a long way. You've made a lot of special tools with extensions on and so on to get the required depth here. So it's pretty straightforward, but you have to remember you're working in 3 dimensions. It's got depth and thickness too. You have to be really careful what you're doing in these sort of phases. It's so easy to wipe yourself out and have to start again with a huge chunk of metal like that. The prospect of that happening would be daunting, to say the least. So you just take things very carefully and plan every move. This shot here is the last of the machining on the underside, or the inside if you like, the inner side of that crankcase half before it was turned over for further machining. The next 4 shots show the machining of the other side, and you can see it's slowly taking shape, all the ribs and so on. They're left full oversize and so on, ready for further finishing work, bosses, etc., or milled around. It's quite a complicated job, but it's getting there. Here you can see a fair bit of scrap being generated. That was about the 3rd time I'd cleaned out that tray, and it is a big tray. It's quite a huge amount of metal that you're removing. By the time I got to this phase, that was more or less the machining. The bulk of the machining done. There were a few finishing off things to do, which we'll go over in the next few pictures. Here you can see spotting through the holes from the other side, the timing side, onto the main, onto the drive side. These are for the bolts that hold the whole thing together, and you can see it's going fairly steady there. And there you get a different view, but you can see quite clearly what's going on there. And really that's quite a large proportion of the machining done. You can see it's getting there. Still a fair bit of stuff to do, but not a massive amount. And at this point I decided to take it out of the machine and have a bit of a look and see how things were looking with it. And here you see it on the table. And the next shot shows the bearing just after it being trial fitted, and that looks good there. And then we go on to what's the next one here? The next one is, we're aligning the mounting lugs. You can see I've got a dummy bar in the milling machine spindle, and I'm lining it up with the hanger on the left hand side of the timing side crankcase half, and I'm going to lock that in position and then put a boring bar in and bore the half round shape in the drive. Unfortunately I don't have a picture of that being done, but it is just basically a boring bar. The top half, the timing side half, is removed after the setup, and the boring bar is inserted, and you machine the mounting lug half round. But you'll see it in other photographs, and you'll see what has been done at that particular stage. In fact, I did actually take a picture of it. You can see the dummy that I used lying in the cuttings, and you can see the cutter immediately above it, forming that half round shape. And this shot is just me admiring the work so far. On the left is the knackered one, and on the right is the one I'm making, and you can see it's coming along nicely. On this shot here, I'm machining the cylinder base flange seating. They're really strange in these old vintage and veteran bikes. They all had very narrow or thin conrods, and they always had a very small gap, and they were strange. I mean, that's you know, obviously that's not milled out fully there, but the conrod didn't have much side play or room for side movement in there, that's for sure. And there's a better shot with the cutting tool out of the way, and you can see it's coming on. It's still not fully finished there. That slot's got to be tidied up. And this shot shows us drilling the holes for the clamps that hold the engine into the frame. Pretty straightforward, really. And this is the final tidying up of the flange, the cylinder base flange, as you can see, and the gap where the conrod goes. And again here we've got another couple of shots of me admiring the work so far. You know, you get to that phase, you've got to have a look at it and examine it and look at it. It just looks good. And here we see a template being used to transfer the holes for the cylinder base across onto the new crankcase half, and you see them being drilled here. Obviously they're tapped after that, ready to take the barrel. And this is the last machining operation, just taking down that gusset or just to finish off the last bits. And that's the machining just about finished, and just trying it out there, looking rather nice. And the next phase is to go on to hand finishing. I say hand finishing, it's not really. I use Dremel and lots of sanding drums to get the blend in all the radiuses, etc. It's quite a big job. And there you can see most of, in fact that's probably at the finished stage of the dremeling work. There's quite a lot of work gone on into that, and I couldn't resist trying it back in to the original piece of metal to show you what is actually hidden inside a big piece of metal. Okay, before we go into any great detail on the crankshaft, first of all, it has to be remembered that in order to make the cases stronger, I wanted to make them an eighth of an inch thicker than the original cast ones, just to be on the safe side. The only way I could get away with doing that was by reducing the thickness of the crankshaft, the flywheels rather, by an equivalent amount. This also meant that I would have to redesign the drive shafts. Well, not the drive shaft, that was fine, but the timing side shaft, because it would have to be an eighth of an inch longer to take up the extra eighth of an inch that was being cut from the thickness of the flywheels. So anyway, the start was made with some, I can't remember what size they are, about 12 inches diameter, EN9, pretty tough old piece of steel. I got it quite cheap as well. I can't remember where from now. I think it may well have been a big lump of bar that was lying on the floor at Metal Supermarkets that I'd seen there up at Gateshead for a long time that no one had taken any notice of. It was rusting away, and I said, hey, can I have a few slices off that? And when he told me it was E9, I said, oh well, definitely I'll have a few off that. And I bought them at a real knockdown price. But here you see the start of it in the lathe. And there you go. The first thing I'm doing is turning the outside diameter down to so that I can actually turn it round in the lathe and reduce the overall diameter. And there you see it in the lathe with the recess for the main journal nut being machined in the rear, or the face of the flywheel. Now what we're looking at here is the same face of the flywheel is actually wrong in the previous statement that was the face. It's not, it's the outside of the flywheel, the outer face. And you're looking at a tapered hole. That is tapered from the large side outside, tapering in towards the bottom of that chunk of material. And what I would do when I make a pair of flywheels that have got a taper fit, I will do both of them and put the tapers in, and then I'll show you, well, if I can on photographs, I'll try and show you what I do to hold them together absolutely centrally. Well, what you have here, or what you're looking at here, is the two flywheel halves bolted, or two flywheels bolted together, with the part you saw in the previous picture at the back. And how I join them together is I make a bolt that has got a tapered head, the same as the taper in the flywheel, and a very close fitting or a very good parallel section on the bolt itself that extends out just beyond the face of the second flywheel. I thread that, and what I do then is make a sleeve, a tapered sleeve that's a tight fit on that parallel portion, but is the same taper as the taper in the flywheel. I then put the flywheels together on that using that bolt, and draw them together as you see in that picture, so that I know that they're both exactly bang on center. With them bolted together like this, I know that they're absolutely perfectly concentric with each other. And the nice thing about it is the large sizes of the tapers are facing out over on the crank pin holes, which makes it nice and easy to turn around to machine on both sides. Another nice thing about this method is that I don't have to alter the angle of the compound slide once I've set it over to the correct taper size, so it stays that way throughout the whole machining process, so I keep that same taper. So we'll carry on with a few more pictures. And here you can see I've machined the taper, and if you look closely you will see the marking blue that's been used to check against the taper of the crank pin. And that once it's at this setting, I don't have to alter it for the other side, which is a bit of a boon. I should perhaps also point out that the 4 bolts you see are actually through bolts, and they will be filled in at a later date so that you have a solid flywheel. In fact, in later pictures you'll see that in evidence. And of course, I forgot to mention that those bolt holes are there purely to hold the job onto the faceplate, because it's the only way you can really hold them on when you're doing the crank pin holes. This shows the other half, the other flywheel separated, and in the machine set up to run true on the 4-jaw, and having the recess machine that was recessed in the face of the first flywheel picture you saw. And here you see the flywheel having its tapered crank pin hole machined. I just unbolted the two and set it up to run true on the outside diameter, and machined that bore. So that was how the 2 crank pin holes were done, and you'll see some other pictures of that fairly soon. And in fact, you can see on this picture that's more or less a finished flywheel. If you look closely at the top left, you can see where the solid, where one of the holes was filled in. Eventually they're all filled in, apart from I think there's one that you use as a kind of alignment hole. Not that you'd ever use it for that. I don't think they're accurate enough for that. But most vintage and veteran stuff seems to have these where you're supposed to stick a bar through and align everything up. It's a laugh, it's a hoot trying to do it. It doesn't work. And here you see one of the last operations being carried out on the machining of the flywheels, which is the counterweight or the lightning side of the flywheel. Not much material taken out there. It's probably horrendously out of balance, but you know, they're very low revving engines, so they're pretty forgiving in that respect. So, but I wouldn't even attempt to try and balance an engine. Well, I'm not going to go into any great detail on making the crank pins and the main journals, but suffice to say that these pictures you're looking at here, or this picture, is them being heat treated in my gas furnace. As you can see, it's just a simple propane torch fed into the furnace, so the flame swirls around, and it's got a pyrometer in there which reads the temperature, and I think if you look close enough you might see 800 or 900 degrees Celsius on that gauge at that time. That's case carburizing, getting them nice and hard, ready for grinding. Here you see the crank pin and the two main journals following heat treatment. They're nice and hard. They were then ground to finish, and any subsequent pictures you see of them will be of them post grinding, so they all look nice and bright. Here you see a test assembly of the flywheels, main journal in there. I'm preparing in general to get everything trued up and ready. And here you see the completed crankshaft assembly, complete with cast iron piston, ready for assembly into the engine. Just to keep myself active while I wasn't doing anything, I managed to start the finishing of the crankcase half, and there you see the main bearing stroke clutch actuator in position in the new flywheel crankshaft half. Now, quite a long time ago, I used to organise a model engine event at Old Warden in Bedfordshire before the magazines took it over and called it their creation, a bit like Donald Trump does with everything. Anyway, one of the guys there, a fantastic engine builder, his engines looked superb, and they always had lovely finishes, and I couldn't, everything looked like cast, and I said to him, well, how on earth do you get that, if they're not castings, what do you do? He said, oh, you just shot blast it, different medium, get a different texture on each piece of metal. So this is what's been done here after everything's been dremeled down and all the machine marks are out. It's been blasted with quite a coarse grit, and it gives that nice finish, as you can see there. And you can see also the next couple of pictures, the cases, and the engine itself being built up prior to being taken down to Kent's place in Fleet in Hampshire. And here you see the engine as built up with a water-cooled cylinder on it, and eventually back in the forecar, and some pictures of the forecar just prior to the veteran run to Brighton.